The history of aviation safety is bifurcated by a single invention, the Link trainer. Before 1929, flight training was an empirical, high-risk activity conducted exclusively within the airframe of an operational aircraft. The acquisition of piloting skills was constrained by weather, mechanical availability, and the inherent danger of exposing novice operators to complex aerodynamic forces. Edwin Albert Link, 1904 to 1981, introduced a fundamental paradigm shift: the dissociation of flight training from the flight environment. Link's contribution was not merely the construction of a training device, but the synthesis of existing industrial technologies, specifically low-pressure pneumatics and electromechanical relay logic, to replicate the control loop of an aircraft. His Pilot Maker was the first successful application of ground-based simulation to solve the physiological and cognitive problems of instrument flight, IFR. This analysis examines the engineering evolution of Link's devices, from the early organ-based prototypes to the mass-produced ANT-18 blue box of World War II. It explores the operational crisis of the 1934 airmail scandal that necessitated its adoption, the specific mechanical subsystems that generated synthetic motion, and the standardized curriculum that trained over 500,000 Allied pilots. Edwin Link's engineering vernacular was derived from the Link Piano and Organ Company in Binghamton, New York. The automated musical instruments manufactured by his father utilized a complex system of pneumatic logic that predicted electronic computing. These instruments, such as the theater pipe organ and the player piano, operated on a binary input system, a perforated paper roll. The presence of a hole in the paper roll exposed a tracking bar to atmospheric pressure. This pressure differential triggered a valve, allowing a stored vacuum to collapse a leather and wood bellows. The mechanical energy generated by the collapsing bellows was linked to a hammer for a piano or a pallet valve for a pipe organ. Link recognized that this valve and bellows actuation system could be scaled up. Instead of striking a piano key, a larger bellows could exert enough force to displace a wooden fuselage mounted on a universal joint. The response time of pneumatic systems, while slower than modern hydraulics, was sufficient to mimic the relatively sluggish control response of 1920s biplanes. In 1927, Link began construction of the prototype in the basement of the factory. The device consisted of a stubby wooden fuselage resembling a generic monoplane, mounted on a universal joint. The motion system was purely pneumatic, powered by a 1/2 horsepower electric suction pump located in the base. The control logic was a direct mechanical linkage, pitch simulation. The control column, stick, was connected via cables to a pair of regulating valves. Pushing the stick forward opened the valve to the rear bellows, venting the vacuum and allowing gravity to drop the nose. Pulling the stick back applied vacuum to the rear bellows, collapsing them and pitching the nose up. Roll simulation. A similar set of lateral bellows controlled the bank angle. Yaw simulation. Unlike the pitch and roll axes, which had limited travel, the yaw axis required 360-degree rotation. Link utilized a pneumatic turbine motor, identical to the motor used to spoil the paper roll in a player piano, geared to the central pedestal. Pressing the left rudder pedal opened a valve to the turbine, driving the fuselage in a counterclockwise rotation. This prototype, patented in 1930, U.S. Patent 1,825,462, was titled Combination Training Device for Student Aviators and Entertainment Apparatus. The inclusion of entertainment apparatus reflects the initial market rejection by the aviation community. Early units were sold to amusement parks to generate revenue for the Link Aeronautical Corporation. The catalyst for the military adoption of the Link trainer was the airmail scandal of 1934. Following the cancellation of commercial airmail contracts by President Franklin D. Roosevelt, Executive Order 6591, the U.S. Army Air Corps, USAAC, was ordered to assume domestic airmail operations. The operational readiness of the USAAC was optimized for visual combat maneuvering, not all-weather logistics. Military pilot training emphasized formation flying, gunnery, and aerobatics in visual meteorological conditions, VMC. Few Army aircraft were equipped with gyroscopic instruments, and few pilots were proficient in their use. When operations began in February 1934, the Air Corps suffered a catastrophic attrition rate. In the first 78 days, there were 66 major crashes and 12 pilot fatalities. The primary cause was spatial disorientation due to loss of visual horizon in fog and snow. The pilots were physiologically incapable of distinguishing gravity from centrifugal force without visual references, leading to graveyard spirals and controlled flight into terrain, CFIT. In 1934, the Army Air Corps agreed to evaluate Link's device. The demonstration took place at Newark Airport, New Jersey, a designated hub for the developing radio range network. On the day of the assessment, the region was under instrument meteorological conditions, IMC, with near zero visibility. Edwin Link flew his personal Cessna C-1 from Binghamton to Newark, navigating solely by reference to the Department of Commerce radio beam. His arrival in conditions deemed unflyable by the evaluating officers served as a proof of concept for the utility of instrument training. The Army immediately purchased 6 Model C-3 trainers. This acquisition marked the transition of the device from a novelty to a piece of essential support equipment. The Model C-3 introduced the integration of radio aids, allowing pilots to practice the specific procedures required to navigate the Federal Airways system. The ANT-18, Army-Navy Trainer Model 18, known as the Blue Box, became the standard production model during World War II. It was a sophisticated analog computer that simulated the aerodynamics of a generic basic trainer, similar to the North American T-6 Texan. The heart of the ANT-18 was a heavy-duty vacuum turbine located in the stationary base. This pump maintained a system-wide static pressure differential. Main supply suction. The pump was calibrated to provide a suction of approximately 3.5 to 4.25 inches of mercury in whole degree. This high-volume, low-pressure air was routed through a main manifold to the various actuators. Instrument suction. A separate regulator stepped the pressure down to 1.9 inches of mercury to drive the gyroscopic instruments, artificial horizon and directional gyro, mimicking the Venturi tube or vacuum pump on a real aircraft. The fuselage was supported by a universal joint and 4 large bellows, 2 for pitch, 2 for roll. Valve assembly. The stick and rudder pedals were mechanically linked to a distribution valve assembly. The valve design was critical. It did not merely open and close, but provided variable airflow to allow for smooth, proportional control inputs. The turning motor. The yaw mechanism in the ANT-18 was a complex assembly of 10 small bellows and a crankshaft, known as the turning motor. When the pilot applied rudder, the valves sequenced the inflation and deflation of these 10 bellows, driving the crankshaft which rotated the trainer. This pneumatic motor provided continuous 360-degree rotation capabilities. Stall buffet. To simulate the pre-stall buffet, a dedicated valve and motor assembly introduced a rapid, oscillating vacuum pulse to the main bellows when the calculated airspeed dropped below the lift threshold. This caused the entire trainer to shudder physically, providing tactile feedback to the pilot. A major engineering challenge was transmitting the attitude of the trainer, pitch, bank, heading, to the instructor's desk without using heavy mechanical cables that would dampen the motion. Link utilized the Telegon system, an early synchro-style electrical transmission system. Telegon oscillator. Located in the base, this vacuum tube oscillator generated an 85-volt alternating current signal at 700 to 800 Hz. Operation. Sensors inside the fuselage detect the position of the trainer and the simulated instrument readings, e.g., altitude, airspeed. These sensors transmitted electrical signals via slip rings to repeater instruments on the instructor's console. This ensured that the instructor saw exactly what the pilot saw in real time. The ANT-18 included mechanisms to simulate environmental variables. Rough air generator. This was a mechanical cam operated by the instructor. When engaged, it disrupted the smooth flow of air to the bellows, introducing random disturbances in pitch and roll to simulate turbulence. This forced the student to scan instruments rapidly and apply corrective controls while fighting physical distraction. Wind drift. The C3 and subsequent models featured a wind drift mechanism in the base. This electromechanical computer offsets the motion of the course plotter, the crab, to simulate crosswinds up to 60 miles per hour. The effectiveness of the Link trainer relied on the closed-loop feedback between the student in the box and the instructor at the desk. Navigation training required a precise record of the student's ground track. Link developed a three-wheeled, motor-driven plotting device called the automatic recorder, colloquialized as the crab. Mechanism. The crab was placed on top of a glass-covered map on the instructor's desk. It was electrically connected to the trainer's heading and airspeed systems. Operation. A synchro motor turned the crab's steerable wheel to match the trainer's magnetic heading. A separate motor drove the wheels forward at a speed proportional to the simulated airspeed. An inked wheel traced a red line on the map, creating a permanent record of the flight path. Error detection. If a student failed to correct for the simulated wind drift or flew the wrong heading, the red line would deviate from the desired airway. This provided irrefutable objective data for the post-flight debriefing. The instructor's station was equipped with a radio simulation console. This allowed the instructor to act as air traffic control, ATC, transmitting voice clearances and weather updates to the student's headphones. Crucially, it also generated the audio signals for the low-frequency radio range, LFR. The primary pedagogical function of the Link trainer during the 1930s and 40s was teaching the radio range system. This navigation system, now obsolete, relied entirely on auditory interpretation. The low-frequency radio range, LFR, consisted of ground stations transmitting directional signals organized into 4 quadrants. The A quadrant transmitted the Morse code letter A dot dash. The N quadrant transmitted the Morse code letter N dash dot. The beam. In the narrow zones where the A and N quadrants overlap, the signals interlocked to form a steady 1020 Hz tone. This continuous tone indicated the aircraft was on the beam. As a pilot deviated from the beam, the steady tone would degrade. Twilight zone. Slightly off course, the pilot would hear a dominant steady tone with a faint static background of either A or N, indicating which side of the course they were drifting toward. Bi-signal zone. Further off course, the two signals became distinct. Cone of silence. Directly over the station, the signal would drop out completely. This cone of silence was the only positive fix that confirmed the aircraft's exact position. In the Link trainer, the instructor manipulated the volume and mixture of the A and N signals based on the position of the crab on the map. The student had to interpret these auditory cues to visualize their position in space, a cognitive load that often induced vertigo when combined with the physical motion of the box. Standard procedures taught in the trainer included orientation, determining which quadrant the aircraft was in; bracketing, using turn and bank maneuvers to intercept and hold the beam edge; procedure turns, a standardized reversal maneuver, typically 45 degrees off course, fly for 1 minute, 180-degree turn, to re-intercept the beam for a final approach. Following the outbreak of World War II, the demand for pilots exceeded the capacity of traditional instruction. Link Aviation Devices, Inc. scaled production to industrial levels. Materials. To conserve strategic materials like aluminum for combat aircraft, the Link trainer remained primarily constructed of wood, leather, and brass. The fuselage was built of plywood and fabric, similar to early aircraft construction. Volume. At peak wartime production, the factories in Binghamton, New York, and Gananoque, Ontario, delivered one trainer every 45 minutes. Total production of the Blue Box series exceeded 10,000 units. The Army Air Corps institutionalized instrument proficiency through the issuance of the Green Instrument Card. Possession of a green card was a prerequisite for pilots to act as pilot in command of multi-engine combat aircraft. The Link trainer was the primary gatekeeper for this qualification. The standardization provided by the Link syllabus ensured that a pilot trained in Texas could fly an instrument approach in the European theater using identical procedures. Recognizing the need for long-range bomber crews to navigate by stars, Link developed the Celestial Navigation Trainer, CNT. Structure. The CNT was housed in a 45-foot-tall silo. It contained a large fuselage enough to accommodate a pilot, navigator, and bombardier. The dome. A collimated light source projected the celestial sphere onto a rotating dome above the crew. The dome moved in synchronization with the simulated time and geographical position. Crew coordination. This device allowed the navigator to take sextant shots of simulated stars while communicating course corrections to the pilot. It was the first instance of Crew Resource Management (CRM) training, integrating multiple flight crew members into a single simulation loop. The end of World War II coincided with the advent of the jet age. The pneumatic mechanisms of the ANT-18 had inherent latency. The time between a control input and the bellows response was measurable. For propeller-driven aircraft, this latency was acceptable. For high-speed jet aircraft, which required rapid control inputs, the pneumatic delay resulted in negative transfer of training, teaching pilots reflexes that could be fatal in a real jet. In response, Link Aviation pivoted to electronic computation. The C-11 trainer. Designed for the Lockheed F-80 Shooting Star, the C-11 utilized analog computers to calculate flight equations. It replaced pneumatic bellows with hydraulic servos and electric motors, significantly reducing latency and increasing fidelity. Digital simulation. By the 1960s, the company, then Link Group, General Precision Inc., was developing digital simulators for the Apollo space program. The Apollo Lunar Module Simulator, LMS, utilized complex digital algorithms to simulate the physics of lunar landing, a direct lineage from the analog logic of the blue box. Edwin Link's blue box was a triumph of mechanical engineering applied to human factors psychology. By isolating the variable of instrument interpretation from the variable of aerodynamic danger, Link created a controlled environment where the counterintuitive skills of blind flying could be drilled to the point of reflex. The technical architecture of the ANT-18, vacuum bellows, telegon oscillators, and the mechanical crab established the fundamental components of all subsequent flight simulation: the motion base, the instructor station, and the visual/instrument feedback loop. While the technology has shifted from leather pneumatics to digital code, the systemic approach to pilot training remains unchanged. The Link trainer standardized the pilot's mind, transforming aviation from an art form connecting on instinct into a profession governed by procedure and instrument verification.